here to thank the organizers, Professor Hong and Dr. for organizing this workshop and inviting me here. KAIST, where I like. And I'm so pleased to stand here and have a chance to tell you about my recent work about combinatorial rigidity of three-dimensional simplicial polytope. But I suppose from yesterday your brain may fit the sense of topology or geometry, but I think my talk you don't need the deep knowledge of topological or geometrical knowledge. I mean, so this program, what I'm going to tell you today, is so pure, is so combinatorial. So I hope you to have an open mind to combinatorics now. Okay, so I also have to tell you that this work is joint work with Dr. Jang-Soo Kim. Okay, so I'm beginning my talk with the motivation. Okay, so let me introduce the notion of Combinatorial manifold, so which is 2D-dimensional smooth compact manifold. If there is a half-dimensional compact torus section, which is locally standard, and its orbit space can be identified with simple polytope. The notion of combinatorial manifold is so I mean, in this workshop, nobody introduced the combinatorial manifold so far. But maybe I think you adjust this notion. But this is nothing but the topological generalization of toric, projective toric manifold. So as some guys mentioned already. So if there is a projective toric manifold, then there is algebraic torus section, right? Then we can think we can restrict the action of compact torus. Then this compact torus also acts on this manifold. Moreover, we have some momentum map. So we have some moment maps whose image is simple polytope, as many guys already mentioned. So by taking and moreover, we can easily check that this action is locally standard. So by taking these two properties, we can generalize. We can think the combinatorial manifold. We can define combinatorial manifold, which can be seen as a topological generalization of projective toric manifold. Okay, but anyway, here we think if we think the projective manifold, then we have to consider the geometry of simple polytope, right? So in the previous many talks, so we have to consider the slope for the various point. We should think, but I want to forget any geometry. So I mean, I just think I just regard this simple polytope as combinatorial polytope. So we only think the combinatorial structure of this polytope in this talk. Okay. So one more thing. So as you know, there is a natural bijection between simple polytope and simplicial polytope. The simplicial polytope is a polytope whose the phase structure is a simplicial complex, has a simplicial complex structure. So there is the natural one-to-one bijection between the simple polytopes and simplicial polytope via the dual map. So if we take a simple polytope here, I denote each dual polytope is P star here, like this one. So I want to, so since this is bijection, so and I consider only the combinatorial structure of polytope. So I want to tell you in terms of only simplicial polytope, because so maybe the simplicial polytope can be generalized easily, and there is some the benefit to to express argument. So in this talk I would like to tell you in terms of simplicial polytope.
What's the definition of simple polytope?
Simple polytope?
Yeah.
Simple polytope is, so if of dimension simple polytope of dimension n is at each vertex there is exact n basis meeting. So why is simple? Then if you consider the ball and make a cut arbitrarily and to make a polytope, then maybe you can easily think that the all vertex there at all vertex there are exact n faces, right? So we say this that kind of polytopes is called simple polytopes.
This dual map means that
so
changing facet into vertex.
yes, so
So for changing the four-dimensional face into a vertex.
yes, for instance, this is a simple polytope because at each vertex there is the exact three faces, but pyramid, and this is not simple polytope because this vertex there is four faces.
difference between simple and simplicial.
Yes, different. The simplicial polytope is the all faces are simplex. So
But if you take the dual, then this is
yeah,
simplicial.
take dual. Then if you take dual, then you can get simplicial polytope from simple polytope. So this is the bisection. Okay, so okay, let P be simplicial polytope. With n vertices. So as a dual, this is in simple polytope notation. This is the d dimension. So d-dimensional simple polytope with n faces. Actually, so okay. In this talk, I will use this notation. Yeah, combinatorialists prefer to use this notation. So and M is a quasi-occurring manifold. over a dual of this simplicial polytope, then it is known by Davis and Januszkiewicz. The equivariant cohomology of this quadratic manifold can be identified. This definition of this one. The equivariant cohomology of this quadratic manifold can be identified by the phase ring. So moreover, so there is a map, the natural projection from this space to BT. So we have the equivariant cohomology ring has the BT module structure via the perfect map of P. Moreover, everything are generated by the degree 2 elements. So this module structure is free. We know that this is free module structure. So its equivariant cohomology ring, as I tell you, this is GP, is isomorphic to the tensor product of cohomology ring of M and A star BT, right? So this is the phase ring of P. So I forgot the names, but some guys have proven that the all simplicial complex can be distinguished by their phase ring. So this contains all information of combinatorial structure of P. So and this is isomorphic to these two rings. So we can conclude that the cohomology ring of M also contains some information of P, right?
Isomorphic is not a motion or additive.
Yes.
Not additive.
It's tensor over what?
Tensor of S BT.
Tensor over.
Over
Z.
Q.
Z.
G. Oh. Z. Yes. Use Z. G. So yeah. So the purpose of this problem is which, roughly speaking, so can cohomology ring determine the combinatorial structure of each orbit space? But unfortunately, it does not hold in general. But some case, the P, the combinatorial structure of P can be determined by this cohomology ring. So the simplicial polytope P is said to be cohomological rigid if it supports a quadratic manifold and so this is simplicial polytope. there is some simplicial polytope Q, which supports another quadratic manifold whose Combs ring is isomorphic to M, then we have combinatorial equivalence between P and Q. Then P is cohomological rigid. We call P is rigid. Actually, this definition appeared by Dongyap-san and Masuda in terms of toric, bands. So because at the first they defined this notion on the toric manifold, but now I hope now we use the quadratic manifold for the definition of cohomological rigidity.
So you mean that this case also you consider 10 also?
Yes.
Because this is 1
Yes. So not the fan, but we forget the geometry of fan. Just the combinatorial structure of fan. Okay. So moreover, I and Taras and Dongyap have proved that if there is two quadratic manifolds over P star and Q star respectively, and if their Combs ring is isomorphic as a graded ring, then we prove that all bi-graded Betti number are the same. The bi-graded Betti numbers, I'm going to define the bi-graded Betti number now. So bi-graded Betti number is the Betti number of Toric algebra okay, this is a base ring with the Q coefficient, but it looks so difficult, right?
Once you wrote rank, you could have put Z as well.
Huh?
Once you wrote rank, not D, but rank.
Right.
See, it's okay with Z.
Yes. So, dimension. Okay.
Dimension.
Okay. So I don't want to explain carefully here. But another definition is equivalently. This is nothing. So this is also. The GP is moment angle complex. This is the GP here. GP is the moment angle complex of P, or by Hochstar. This can be understood by this way. So let me tell you what these notations. So VP here, VP is the set of vertices, and P P restricted by W is a realization of full subcomplex full subcomplex induced by W in the phase structure. As I told you, phase structure is simplicial complex. It has a simplicial complex structure, so this can be defined here. Okay, but still it looks so complicated, right? So, but this can be understood in combinatorial way. So later I will tell you again this definition later. Okay, so as we know this theorem, so let me define the combinatorial rigidity of simplicial polytope here. So definition. So P is combinatorially rigid, so, or simply just rigid if we have the combinatorial equivalent between P and Q for any Q satisfying all petty numbers are the same. So moreover, I have a remark. So if P supports a Toric manifold and P is the combinatorial rigid, then we know P is cohomological cohomologically rigid. So the question, the main problem in this what I'm telling you today is which polytope can be combinatorial rigid. So it is induced that which polytope can be cohomologically rigid. Actually, in general, the Lie group action on manifold is independent on the combinatorial structure of orbit space. But in this case, so there are. If P is combinatorial rigid, then it is quite related on the cohomology link of the supporting quadratic manifold. Okay.
Delta is some kind of error of Hatch number.
Hatch number?
Hatch number? HPQ something like that.
I don't know. No, he said.
Different.
So
Suyoung, before you go on, I want to ask you a question.
Okay.
So just now you said the theorem says if the cohomology ring of M and N are isomorphic, then the phase number is the same. And just now you wrote the phase ring is isomorphic to the
yes.
To this cohomology ring tensor product with
Yes.
BT.
Yes. But
But this does not imply their phase ring are isomorphic. Huh? Yeah, it's isomorphic to the tensor product.
Yeah, that's as additive to this, not as a ring.
Oh, okay, nice.
okay. Okay, so let me introduce some no-rigid polytopes first. So I will tell you both the simplicial and simple polytope version. So every polygons are the rigid polytope, and the join of the boundary of simplicis also the rigid, which is dual of product of simplexes.
It's not polytope. On the left hand side.
Sorry?
On the left hand side, that's not a polytope. But okay.
I see.
I do understand what you mean, but maybe other people who would not. That's not a polytope, right? That's just a simplicial complex.
Yes. So feel
It's a boundary.
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 feel the inside. Yes. Right.
Corners.
Yes.
What's the start? It's top.
It's joined. So yes. Okay, moreover, the context cut of this one. This is nothing but also nice. Okay. So okay. They are not only cohomological rigid but also combinatorial rigid, and moreover, they are all support the quadrature manifolds.
The converse is not true, right?
Sorry? Yes, converse is not true.
So million plus also.
Exactly. We don't know whether it is the converse true or not, but I strongly believe the converse is not true, so we don't have any counting example so far.
There exists a polytope which has two different polytopes with the exact same Betty number. Two different polytopes with the same Betty number.
Betty number.
Yeah, bi-graded Betty numbers. But
Betty number is a hot number.
no, bi-graded Betty number.
Yeah, this one.
But the question is, it does not clear whether they support quasi-Tory manifolds where the cohomology rings are.
Yes, so actually, so far we don't know whether the converse is true or not, but I think it is not true. Okay, so from now on, I'm going to tell you about the three-dimensional case. So if J minus I is greater than or equal to 3 or less than or equal to 0, then beta ij is 0 except for only this case. So since this is three-dimensional case, so you look the Hochster formula, which I wrote here, wrote before, then you can easily check that the all Hochster theorem Hochster formula is written in terms of the reduced homology of some sub-polytope. So you can easily check that this one. And moreover, there is a duality. Like this way. So you can see that the difference of these two values are 1 and the difference of these two values are 2. So the distance of the distance of is greater than or equal to 3 or less than or equal to 0. Then we know everything. But and moreover, there is the duality between the difference 1 and 2. So we just consider only
So here n equals 3, n equals to 3.
Yes, this is the dimension is 3 case. D is 3. Here, n is the number of cases, number of vertices.
Okay.
Yes, so we only need to consider the beta I minus 1 I of P, right? To know all Betti numbers of given simplicial polytope. So we define, we denote this by BIP, and we call this number is special Betti number, bi-graded Betti number. Okay, moreover, this bi-graded Betti number can be understood in purely combinatorial way of P. Purely combinatorial way as follows. That is, so if you look the Hochster formula, so simply this is this one. So here BI case the J is the I minus, sorry, here J is I and I is I minus 1. So this is the zeros, the reduced homology of P bar W. So this means the number of connected component, right? So minus 1, yes, connected component minus 1.
This H0 is the ordinary simplicial homology. This here.
Yes, ordinary. So this is nothing but CC means the number of connected components. Okay, so moreover, I'm defining the notion of the connected sum. So let P1 and P2 is a simplicial polytope. But here we don't need to assume that the dimension 3. So here dimension D. Then a connected sum connected sum of P1 and P2 is a polytope obtained by attaching a phase sheet of P1 and a phase sheet of P2. So remember that all phases of PIs form the simplex. So if we choose any phases from P1 and P2, then we can identify them, right? So we can attach this phase and this phase, then we get some another polytope. So this is the connected sum of P1 and P2. And I denote P1, P2 is the set of all connected sum of P1 and P2. So the connected sum is depend on the choice of phases and how to identify them. So there are several polytopes which is a connected sum of given two polytope P1 and P2. So I denote P1 sharp P2 is the set of all connected sums. Okay, let me give you some example. Let me give you some example. So if P1 is just simplex, and P2 is just simplex, okay, then P1 connected the connected sum the sum of these two polytopes is this one, right? So this is P1 and P2, and choose P1 and choose P2, and attaching this polytope to P1, then we get this polytope, right? So this is the as dual, this is nothing but equation. Okay, so now we can compute the special Weierstrass number here. So B2 is the sum of all connected components of P restricted by W minus 1, right? So so if connected component is 1, then it has no meaning. So we can consider, we only consider the pair of two vertices which is not connected, right? So then here there is only five vertices. Then there is only one pair. There is only one pair, this one and this one, which are not connected, right? So B2P is 1, and if you choose more than or equal to 3 phase vertices, then they are all connected, right? So they are all 0. So you can notice that this computation of Bible-Betty number is so combinatorially. Okay, so okay, so if P is in the connected sum of 2 polytopes, then P is called reducible, and if otherwise, P is called irreducible. Okay, so the purpose of this talk is to find all reducible simple reducible rigid simplicial polytopes. Yeah, because because the first non-rigid simplicial polytope or simple polytope is the first example of non-rigid polytope is reducible. So that's why we are thinking this problem. Okay, so I have proposition. So P is in the connected sum of P is rigid. So P is a connected sum of P1 and P2, and P is rigid. Then this set must has only one element. So because so this has N1 vertices and this has N2 vertices, we assume. Then here these 3, right? Sorry. So if P is connected sum of 2 polytopes P1, P2, then the special Bible-Betty number of P can be computed by only the information of BIs and the number of N1 and N2. So this means the P is independent of the special Bible-Betty number of P is independent of the ways of connected sum. So this implies that if P is rigid, combinatorial rigid, then this set must have only one element.
Before you proceed, could you also write similar formula for the other Betty numbers of the connected sum?
I don't have. So only this case. Because this case it can be computed in combinatorial way very easily, yes, easily. But the other case is we have to consider the high dimensional spheres, so it's not so it's not easy.
Excuse me. It's a BKB?
Sorry?
This formula is which
Sorry, BK. Yes, BK.
You know there you have D, right? Instead of 3. That's the only.
Yes, in other dimension, then you just change your the D.
You write it all for the D instead.
Yeah, dimension D, then this is D, and this is 2D. It can be changed. But other dimensions, this formula holds, but it doesn't imply this one. Okay.
Because you have more better numbers.
Yes, we have more better numbers. Okay, so we have some proposition. If P is a connected sum of more than or equal to 3 polytopes, then P is rigid if and only if P is the connected sum of 3 tetrahedrons. Actually, in my plan, I want to give a proof of this proposition because it's very interesting, but because of time, I omit.
So what is this? Can you draw it?
This one.
Yeah.
So
Can I add one more? So what is this?
Cut one vertex.
So what is this? This is how many faces does it
this
have?
one. So
Okay, so
in simplicial version, this is the vertex cut of
Okay. 8. How many faces does it have?
5.
No, 1,
6.
6. Vertex cut of
Actually, this is the product of two simplex, and this is vertex cut.
Vertex
So
cut.
this is rigid. So the conclusion is to find all reducible rigid polytope, we just consider the connected sum of two simplicial polytopes, right? Because if there is 3, then we know the only possible case is so the base lemma is if this set has only one element, then P1 must be Platonic. Platonic means the regular polytope, and Q is phase transitive. Phase transitive means all P2. Sorry, P1 and P2. Or automorphism preserve the phase structure. Is phase transitive. So moreover, this is by place, no, and image. I don't know how to read it. Image. They found all phase transitive polytope. The P is either the bipyramid or Catalan polytope. So the picture of these polytopes, you can find your abstract.
This was dimension 3, right? Dimension 3.
Yeah, dimension 3. Yes. So maybe I hope all of you have. Yes. So the first picture, the figure 1 is a prism, and the second one is a semi-bipyramid, and the other 6 polytopes are all Catalan polytopes. Actually, they don't assume the simplicial polytope first. So
This is
So there are more Catalan polytopes in general, but I choose all simplicial Catalan polytopes. So that is only 6 of 6. These 6 guys and the Platonic polytope.
so. In other words, you have those two are the Platonic, which is not simplicial, not simplicial, and then you take what is that? This is what's division? What is that?
Yes, yes. So the second one is the bicentric subdivision, and
Pericentric? No, it's not pericentric.
the second one,
No.
the last one. I mean, the last
Yeah,
one.
last one.
But the middle one is, I don't know the name in general. So in our papers we just give a name. So actually there are a few essentially there are a few polytope can be Catalan polytope. So there are, if P is reducible rigid, then P is either T4 or connected sum of the tetrahedron octahedron and icosahedron, or bipyramid. Bipyramid is dual to the prism, and there are 4 polytopes. I just say A, B, C, D. The 4 polytopes. So this is the possibility. I cannot say they are all rigid, but they are only candidate to be a reducible rigid polytope. So this is the theory. We don't need to think of this case. So
you are taking the connected sum of those.
yes. So the next step is which polytope can be rigid, right? So in our calculation, so this and this and this and this one and this one are rigid, but we don't know the other case so far. But actually, so these 14 cases are finite case. Just we know the exact polytope. So if we have enough time and enough good computer, then we can prove whether they are rigid or not. But this, I want to solve only this case. So this is the most difficult part. So I don't give the full proof of which polytopes can be
Well, I mean,
rigid.
even though what do you have to show that they are rigid or not? What do? Do you use the computer?
Yes.
Because you can calculate the graded Betty numbers of these, but how do you know that?
Since we know the number of vertices, then we can generate all vertices and all polytopes which have same vertices and compute all binomial Betty number and compare it. Then you can do it. I mean the concept. Of course, if we find more efficient way, then it's good. But actually, I mean, if we have enough time and good computer, then I mean we can prove it. But this case is not, because these three cases are depend on the vertices. So this is infinity case. So we need the more efficient way to know of it. So I will tell you the basic idea of these two guys. So, but it is not so difficult. So this is the pyramid. Pyramid due to prism. You can find the figure in your abstract, and BM bar is a semi pyramid.
What do you mean by semi pyramid?
This is the dual of edge cut of prism.
Which edge?
So the
base or the top one? Side one?
Yes. No. Top or bottom one. Because side, if you edge cut on the side,
it increases. Just another BN.
Yes. Yes. Okay. Then, moreover, note that if P is irreducible, then then the Bn minus 4 P is the number of 4 belts. I mean, if you have some simplicial polytope here, then you choose n minus 4 vertices, then this means you don't choose 4 vertices, right? Right? So if this choice has meaning, if and only if, as I told you, if and only if this is disconnected, this means these 4 belts divide this P into 2 parts, right? So the Bn minus 4P is nothing but the number of 4 belts, like this one, right? So if you look at the figure of by pyramid, then you can easily guess that there are many. So there are, Bn and Bn bar have many cobelts. Right? So we prove that the Bn minus 4 of other polytopes having n vertices is less than the Bn minus 4 of Bn bar, and it is less than Bn minus 4 of Bn. And using this lemma and compute the Bn minus 4 of this size and comparing with other cases, so we can conclude that these two cases are all rigid.
So P is, do you know, P is irreducible implies Bn minus 4 is sharp number of products, or do you need indivisibility?
Yes, so
This comes from, how's the,
I mean, if reducible, then there is a 3 belt. So if you choose 3 belt and one other polytopes, other vertex, then since it is not 4 belt, although this is not 4 belt, but it affects the BMS 4, compute BMS 4. So yeah, that's case. So this can be so. Another corollary is the pyramid and semi-pyramid, or both pyramid and semi-pyramid are also combinatorial rigid here. So anyway, as another corollary, so by Kao and Professor Jiryu, so they proved that overall prism, all small covers can be distinguished by their G2 Cohomology ring. Sorry? Yeah, cohomology rigidity. So then, in this case, you can remove the condition of the orbit space. Yeah. Okay, I'm going to stop here. Thank you.